morning. It's almost lunchtime, so I'll try and move along quickly, although I'm here to talk about 25 years of experience doing groundwater recharge, and that's hard to fit in 15 minutes. So here today to talk about the Milton Quarry and a groundwater recharge system. This is a project which got me introduced to Steve Hollish, as it was my job to go and meet with Steve in the late 90s to convince him that we knew what we were doing and we could develop a new area of the quarry and still protect the water resources that surrounded the site. The Milton Quarry, if you're not familiar with it, it's one of the largest quarries in North America and sits just north of the 401 on the west side of Milton. You'll see it if you're headed westbound along the 401. And importantly, it sits in a natural environment-rich area within the Niagara Escarpment World Biosphere Reserve. So any development within this area obviously needs a very high level of care to protect the water resources. Just a diagram showing the Milton Quarry. The plan in the late 90s was to license the yellow areas, which are to the north in this figure. North is up. And importantly, from a water resources perspective, we had some natural environment features that were very sensitive. The blue highlighted area is 6-line tributary to 16 Mile Creek. It has cold water fish habitat in it, so obviously a key groundwater dependence in that tributary. And there are a variety of wetlands around the site, particularly on the east side. There's a number of wetlands that were breeding pools for Jefferson salamander. So another highly sensitive environmental feature. That's all in addition to a number of private wells in the area. So we had an environment that's rich with water resources that are supporting important ecological features, and we have a relatively shallow water table aquifer within the dolostone that is to be mined. When you're mining dolostone, you tend to want to dewater it. So very early on, we concluded we couldn't just dewater this quarry, let the drawdown propagate, and predict that, well, it shouldn't influence things too badly. We needed to do better than that. We needed to assure the world that we were going to be able to maintain those water resources to prevent any adverse impacts. So we embarked on an extensive set of studies, a whole team from GHD as well as some other consultants who were involved in that. Undertaking those investigations over a number of years. The photo there is a typical rock face within the quarry. It's about 30 meters of exposed dolostone. We've retained the Amabel nomenclature for the site as there's legacy approvals and documents there, and we didn't want to change nomenclature partway through, but that's obviously the Gasport Formation, which is being mined out, and then Dufferin also takes out a couple meters of what we call the Renales Formation underlying the Amabel. So pretty consistent rock mass. There are some reefal features in it which give us some localized lower or higher permeability zones, but as a whole it is pretty bland characteristics in that rock. The early indications we had from the analysis was that it was behaving as a single hydrostratigraphic unit, and that was important to both how we manage the site and how we assess the potential for impacts. One of the key things that was really interesting was we found that groundwater levels vary seasonally by up to 7 meters at some parts of the site where we have a recharge mound. And when you think of that, that's 20 to 30 centimeters a week of groundwater level change happening week after week after week. So it's a key factor that you have to be able to consider within your programs. So our solution to this was to implement a program of recharging groundwater around the quarry excavation. So we're not letting that dewatering influence that would normally occur propagate out to the natural environment features. Instead, we're returning water into the ground to support the groundwater levels. To support this, we took a very integrated approach, combined the water from all the various areas of the quarry, brought it all back to a reservoir that was constructed within the main quarry so that we had assurance that we always had lots of water available to provide mitigation and that we could assure that we had good water quality for those purposes. It also gave us the opportunity to implement a additional storage and discharge capacity so that we could address some of the needs that the region of Halton and Conservation Halton had identified relative to protecting against flooding downstream and low flow augmentation in 16 Mile Creek. As part of the whole package, just as a point of interest, Dufferin has agreed to take 400 hectares of this land and donate it to public use after the fact. So there'll be long-term opportunities for recreation and conservation on these lands in the future. Just a little schematic here I'll skip over, demonstrating how the concept of recharging to groundwater to limit that drawdown influence propagating away from the quarry excavation. Obviously, long-term, we want to be as passive as possible, so once the quarry is finished extraction, quarry cells will be flooded to create a lake, which minimizes the need for active management of the water. So we talked earlier this morning, or heard discussion earlier this morning about the variability of bedrock, and that was obviously a key factor. You know, how do we design a system? How do we predict what kind of recharge system we're going to need, and how are we going to operate it? So we didn't fool ourselves and try and predict exactly how much flow was going to need to go into how many wells at each location. We took an adaptive approach to this, and we did this by putting a series of trigger wells away from the quarry, up gradient of the water resources that we were trying to protect, and we said, okay, we need to maintain natural water levels at those locations, in those trigger wells. And then back closer to the quarry face, we implemented a ring of recharge wells surrounding that quarry excavation area to be able to provide recharge at that location, holding up the water levels at the trigger wells. From a practical perspective, to make that work, we installed monitoring wells adjacent to those recharge wells, fed those water levels from the monitoring well back to a SCADA system, and then automatically adjust the flow into the recharge wells to maintain a set point in that adjacent monitoring well. And that way we know we're maintaining the groundwater level in an area around that recharge well. And over time we fine-tune what that set point is for that monitoring well so that we're maintaining the targets in the trigger wells. All that water is supplied through a buried water main that goes around the perimeter of the site. This is just a photo to give a perspective of the main quarry, and you can see the large reservoir area that was constructed on the left-hand side there. So recognizing that we can't have this system go down because of shortcuts or we implemented a very high level of engineering into this program, akin to really a municipal water supply system where we've got redundant capacity in our pumping systems. You can see a picture there of the pump house that's sitting at the north end of the reservoir, and there's bottom draw intakes drawing water into that pump house, so that we have assurance that we have capacity to operate the system all the time. We can take pumps out of service, those kinds of things, right? Going far beyond what you would normally experience in a quarry setting. The actual recharge component of the system is supported by a water main that runs around the perimeter of the site. So it's about 8.5 kilometers. The system's looped so we can maintain pressure in it just like you would for a municipal water system. And then there's recharge wells following along that water main. We connect up the recharge wells using what we call control huts. And that's just a place where we tap off the water main, come into this little building. You can see a picture of one there. And inside we have all the valving and metering for individual recharge wells. We run water through bag filters in case we get a surge of sediment from the pipeline, et cetera. In terms of actually placing these systems, constructing them, we had a high degree of input from the project ecologist, and we had some of the, I believe it was the Conservation Authority biologists, come out and look at that as those activities were going on. So a very high degree of care to fit things into the natural environment to minimize any disturbance to the features that were remaining around the site. Took an extraordinary level of care and Contractors looked at us cross-eyed as we gave them marching orders. And if you look at the picture, you can see, we're weaving in between trees when we're putting water lines into wooded areas, fencing things off so that we're not damaging trees or disturbing any particularly sensitive vegetation. And then it's all restored afterwards to try and prevent any invasive species from coming into those areas. So a very high degree of care goes into the construction of the system. Now, once it's built, we have to verify that it works as intended. One of the approval requirements is a verification of the system before extraction occurs, so a huge upfront cost and effort. And that verification effort included going in and testing each individual recharge well to make sure it's influencing adjacent wells, and then testing the whole system to make sure that we can influence all the trigger wells that are located beyond the recharge alignment. So we started out with a limited number of wells in the system. We put them at 100-meter spacings. It was an arbitrary round number, to be honest. And then as the quarry developed, the stresses on the system gets larger as you get closer. So we've added more and more wells, and we've ended up, today we're operating at about 165 wells along that 8.5-kilometer perimeter. Just a graph there showing some of the individual verification results. I won't take time to jump into that. So, as we are working with the various agencies to obtain approvals for this site, and we were able to obtain support from all of the agencies, but they did want to have assurance that we were going to do this properly, and didn't want to be in the position of, getting an annual report where we say, oh, last year we had some problems and it didn't work so well. That wasn't going to be acceptable. So Dufferin agreed to providing data in real time to the agencies. So all of the data we collect from this site, and it is a ton of data, goes online on a daily basis, and the agency's technical representatives can go in and look at that data. So it's got water levels for every monitoring well, every trigger well. It's got recharge flows for individual recharge wells. It's got the water level and storage volume in the reservoir. The water chemistry that's collected on a regular basis is all in there in a format that they can review if they have concerns or questions about what's going on. So what have we learned from the last 25 years here, right? Overall, I'd like to say to Steve, it worked, that's been a real success. We figure 99% uptime in terms of aggregating meeting the target levels in all the trigger wells. We do have short-term drops below target levels when we're doing maintenance on a particular component, or when we get an ice storm and lose power for a couple days. But even then, we have a lower bound that we also monitor, and we've only had a couple instances over the last 25 years where we've had a water level drop below that lower bound where we've historically observed water levels at wells. So very good outcome from this system in terms of how it has behaved. And that success and the demonstration of that success to the agencies involved in this allowed us to support Dufferin with the Acton Quarry extension, which was granted a number of years ago, and a similar system has been implemented there. Acton Quarry's maybe 5 kilometers to the north of the Milton Quarry, near the town of Acton. And just recently, the east extension was, what we call the east extension, was approved at Milton Quarry, which is a limited area of open field that's going to be also quarried out in the future. That license was just granted, and it's based on extending this water management system to that area. From more of a hydrogeology perspective, what have we learned? From all the observations we've seen, the Amabel or gas port is behaving as a single hydrostratigraphic unit here. When we get very up close and really stress it, we'll sometimes see some stratification. but really that comes down to very small-scale fracture setups within the rock mass. At the very beginning, Dufferin was using a recharge pond to support water levels, and that was effective in early days, but we found the pond, as the gradient gets steeper, as drawdown and extraction approaches that quarry pond, it becomes incapable of maintaining the water levels throughout the depth of the formation underlying it. They also prone to blinding, right? It's a pond sitting out in the middle of a wooded area. It's got dust, it's got leaves falling in it, so the bottom of that pond tends to blind. With the recharge wells, we've had very good behavior, really next to no challenges using the recharge wells, other than how we can get them in nicely into some of those natural environment areas taking care. But they've worked very well, and we've been able to maintain gradients as high as 1, where we have recharge wells operating very close to the quarry face. So a very effective tool for supporting groundwater levels around the quarry. One area we encountered some very permeable rock where the recharge wells were very close. So we did some grouting in that area, just using Portland cement grout to slow down that amount of recirculation, and that was also effective to help manage that situation without having to just keep adding more wells and higher flows in that area. Key to how this program has worked, and I think the success is Dufferin's willingness to be very proactive on this. So we have always been able to go out and install extra wells ahead of time. We say, you're mining in this direction. We're not at capacity for what we can recharge in the adjacent area, but we don't have enough to make us feel comfortable as scientists and engineers. So we've gone out and installed additional wells ahead of time. We've always made sure that there's enough pumping capacity to increase the flow rates to things, and that way we don't get behind if something changes and we hit a variability in the rock mass or a drought condition that we need to respond to. So being proactive is important, and the MOE has been quite supportive in that, because we had to go to them and say, well, we only need this much water and we only need this much capacity for our ECA, but we want to have this safety factor in case we need to do something. We don't want to have to come back in an emergency situation. And so they were good about giving us large permit limits that we hope to never use, but they're there so that it doesn't slow us down if we need to implement additional measures to make sure we're protecting these water resources. Question that came up a lot when we're going through the approvals is what's going to happen to the water quality. Short story is water quality is maintained good. The reservoir water quality is very close to background groundwater conditions, so we haven't had any issues recharging that water back into the ground in terms of the chemical content, and it hasn't given us problems with clogging or dissolution around our recharge well. So that's been good to confirm. And just to note, we've made a conscious decision throughout this time period to stick with a relatively straightforward modeling tool. I had done enough modeling work by the time we started this in the late 90s that I knew there's always variability in the real world versus the model. So we stuck with a relatively straightforward, steady state modeling approach, and then took all those variables that it doesn't account for and put that into our planning and contingency measures so we could adapt to conditions as they actually occurred, right? And that's made it much more manageable as an analysis tool to let us look at different scenarios in short order and use it as a day-to-day tool. One of the feathers in Dufferin's cap that I'll put out here is, how do we know it works? Well, one of the things that we can look to is the Jefferson Salamander Recovery Strategy document, which specifically looks at the Milton water management system and identifies that it has been very effective supporting the Jefferson salamander population, and recommending it as a tool to be considered in supporting that species. I've included the citation there if anyone's interested in reading that. Throughout this process, we do a lot of science, we do a lot of engineering, we do a lot of construction operations. Always like to go back and remember what we're working to protect. I should have had a water well on this figure, but the site is surrounded by some really stellar environmental features. If you haven't been out in the Milton Quarry area, the Bruce Trail and lots of side trails out there, it's just an absolutely beautiful place to go and explore and enjoy nature. So in summary, as a project, as an undertaking to implement and design and implement this groundwater recharge system, what have we achieved is the question. Foremost, our client's interest was supplying high quality aggregate close to market, right? And that's what Milton Quarry has contributed to Ontario's economy. It's the best dollar stone in the province, and it's as close to market as you can get just off the 401 on the west side of Toronto. And while doing that, we've been able to protect wetlands, cold water fisheries, threatened and endangered species habitat. We've been able to create new wetlands, and with the rehabilitation of the site, there'll be additional wetlands and natural environment features being implemented to go into public use. The public water supplies have been protected, but frankly, in the aggregates business, that's a pretty easy thing to do for private water supply wells. We've provided the region and Conservation Authority those opportunities for low flow augmentation and additional flood protection, and demonstrated that we can take this more active approach to managing a site, providing mitigation to allow a development within a sensitive ecological environment. So I'd like to thank you for giving me the opportunity to talk about this project. It's a quick time for the amount that we've been through over 25 years. So I welcome anybody, if you want to talk to me in the chat or contact me on another day if you're interested or have questions about what we've done. Thank you.